We're continuing on with our study of projectile motion. The next problem we'll do is a golfer wearing a spacesuit at a driving range hits a golf ball so that it leaves the tee at an angle of 42.5 degrees above the horizontal. The golf ball lands at the same elevation 217 meters away. What was the initial velocity of the golf ball? Well, there are various ways to do this one, but for starters, I'm going to start off with another problem and we'll develop a formula that will help us here. A projectile is launched from ground level on a flat plane. It has an initial speed of v0. That didn't grow when I increased the font size. Oh well. And its initial velocity makes an angle theta with the horizontal. So this is supposed to be theta and this is supposed to be v0. How far does it travel before it returns to the ground? So here's the situation. There's our flat plane. We've got something launched at an angle theta with an initial velocity v0. And it's going to travel its parabolic arc and come back here to the ground. And how far is this? This will be the x that we measure, although in this case the distance that it ends up at is also sometimes called r, the range of the projectile. So let's develop a formula for that. Our projectile motion equations are that v sub x naught, or it's v naught x, whatever we call it, is equal to v naught cosine theta, v naught y, I think that's the way I've been writing them, is equal to v naught sine theta. And then we have x is equal to x naught plus v naught, well, it'd be v naught xt, but let's just call it v naught cos theta times t. And y is more complicated. Y will equal y naught plus v naught sine theta times t minus 1/2 gt squared. Okay, now some of these formulas we've developed before, but it doesn't hurt to do them again. First of all, let's let x naught equal 0 and y naught equal 0. We'll just let this spot be our origin right there. Okay, the launch point. Now, let's take a look at what happens when y returns to the ground. Okay, so at that case, well, y naught is already 0, but y is going to be 0 also. So what we'll have is that when y naught, or when the projectile returns to the ground, we'll have 0 is equal to v naught sine theta times t minus 1/2 gt squared. Okay, and we'd like to know how long that thing is in the air. Well, we can factor this expression. It's got t's in both terms. To find the solutions to the time, we'll have t times v naught sine theta minus 1/2 gt. Those multiply together to equal 0. One solution is t equals 0. That's the instant it was launched. The other one will give us v naught sine theta minus 1/2 gt is equal to 0. We can kick that 1/2 gt across. V naught sine theta equals 1/2 gt. Multiply both sides by 2 and divide by g, and we'll get the time of flight will equal 2 v naught sine theta divided by g. Now, we may have written this as 2 v naught y over g in an earlier problem, But for this one, we're going to leave the time as that. Okay, so that's how long the time of flight is. Now, the range that the projectile travels, we can solve this equation for that. Now, x naught is equal to 0, so the total distance traveled, which we could just call x, but we can also call it r, the range of the projectile, is going to equal v naught cosine theta times t. But we found out that the time of flight is 2 v naught sine theta over g, so we can say, I'm just going to write it as the range of the projectile. I'll have v naught cosine theta times 2 v naught sine theta divided by g. Now I'm going to rearrange terms a little bit. I'm going to stick the two v naughts together, and I'll have v naught squared out front, and then I'll take that 2 and the sine theta and the cos theta and that happens to be a trig identity. 2 sine theta cos theta is actually equal to the sine of 2 theta. So here's something about the range of a projectile. As long as it lands and takes off from the same level, its range will be v naught squared times the sine of 2 theta divided by g. Okay. Well, what is a sine function? How might you maximize that? Could you pick some angle that, if you know that your projectile launcher will always fire at the same velocity or the same speed, you can maximize the distance? You'd want to figure out a way to maximize the sine of 2 theta. Well, here's what the sine function looks like. It looks like a sine wave, oddly enough. Okay, there's the sine. I'm graphing the sine as a function of theta, or this could be as a function of 2 theta, actually. Okay, well, this would max out when here you have pi over 4. If this is the sine of 2 theta, actually, we could just have theta on the horizontal axis. Whoops, that doesn't look much like a sine of pi over 4, but that way, if theta is pi over 4, 2 theta is pi over 2, and that's when the sine is at its maximum value. Okay. Pi over 4 is 45 degrees. That means launching a projectile at 45 degrees is how you can maximize the range, as long as you ignore air resistance. But this formula will be useful in solving the golfer problem. So let's have a look at that. We have the golfer wearing the spacesuit. Let's see, it's a projectile motion problem, so I better write those down. It's launched at 42.5 degrees above the horizontal. Now, it may be that when you're hitting a dimpled golf ball, that there are other angles than 45, because air resistance is definitely going to play a role in that case. But anyway, it's taken off at a velocity v naught. We know that v naught x is equal to v naught cos theta, and I'm going to let 42.5 degrees equal theta. V naught y equals v naught sine theta. We can say that x is equal to x naught plus v naught xt, which is just going to be x naught plus v naught cos theta times t. We've got that other complicated thing for y, turns out we probably won't even need to consider that on this problem. Y will equal y naught plus v naught yt minus 1/2 gt squared, which we could plug in v naught sine theta for v naught y. And we can say that v sub y is going to equal v naught y minus gt. Now, we may not need these things because since we know the golf ball lands at the same elevation it took off from, we can use this formula. The range of the projectile is v naught squared times the sine of 2 theta divided by g. Okay, well, we know how far the projectile goes. The golf ball, it lands 217 meters away. We know theta, it's 42.5 degrees, so 2 theta is going to be 85 degrees. We know g, the only thing we don't know here is v naught. So we can solve for that. First I'll multiply out from underneath by the g, and I'll get the range of it times g is going to equal v naught squared sine of 2 theta. Let's see, I know sine of 2 theta, or can plug it into my calculator, so I'll get v naught squared is equal to r times g times the sine of 2 theta, or v naught will equal the square root of rg over sine 2 theta, which is the square root of 217 meters times 9.81 meters per second squared divided by the sine of 2 times 42.5 degrees. Let's calculate that. 46.2 meters per second. Maybe that was too easy once we had this formula. And you wouldn't have known about that, except there is a section, or a small subsection, in the chapter section that's on projectile motion. Toward the end, they do talk about the range of a projectile, and they will have developed that formula. Let's move on to the next problem, the golfer on the moon. Later, the same golfer visits the moon, where the acceleration due to gravity is 1.61 meters per second squared. He tees up and hits the ball with the exact initial velocity that he did on Earth. This would take some kind of luck. Unbeknownst to him, the ground is sloping upward at 5.00 degrees. That's going to toss in a complication, but we want to know how far up the slope the ball is going to land. So let's see what we can do with this. We're given that it has the exact same velocity as the previous problem, so I'm going to make a note of that here. That means the launch angle theta will equal 42.5 degrees. The initial velocity will be 42.6 meters per second. And this is a projectile problem, so we can say stuff like v naught x will equal v naught cosine theta, v naught y will equal v naught sine theta. And if you haven't convinced yourself yet that those are correct, draw yourself a little triangle and just do this. Here's v naught. Here's v naught x. Here's v naught y. And v naught x and v naught y are perpendicular to each other. This is just a magnitude triangle, but it'll work. And then we can also say that x is going to equal x naught plus v naught xt, and y will equal y naught plus v naught, I meant to write x naught plus v naught cos theta times t. And here I'm already doing it in the y thing. Y sine theta times t minus 1/2 gt squared. And I think for this problem, I'm going to let the launch point of the golf ball be the origin. So I can say that x naught is going to be 0 and y naught is going to be 0. I'm trying a new layout here where if I start running out of room, I can move over and finish solving the problem over here. We'll see how that goes. Now, there is one other thing that I know. Wherever it lands over here, I can make a little right triangle. This may not be where it lands, but the distance it travels in the x direction is going to be this far. I'll just pretend that it's launched from exactly that point. And the distance it travels in the y direction will be this little direction. So y over x, we know they're always perpendicular. If I choose my coordinate system carefully, I'm going to have x pointing horizontally, not up the slope, and then I'll have y pointing that way. But when it lands on the ground, I can say that y over x is going to equal opposite over adjacent, the tangent of 5.00 degrees. In one of my earlier attempts on this problem, I put the tangent of theta here, and then I got a little farther along and things just weren't working out. So be careful when you set up a problem like that. It can lead you astray. Okay, well, I'm going to see what I can do with this expression. Tangent of 5 degrees is just a number. And my x and y equations, I'll rewrite them here. X is just going to equal v naught cos theta times t, because x naught is 0. Y will be a bit more complicated. It'll be v naught sine theta times t minus 1/2 gt squared. By themselves, these aren't enough to figure out where it's going to land. However, I do have this. And so I can take this expression and divide it by this expression, and that'll equal the tangent of 5 degrees. That's a third equation. Let's see what we can do with that. V naught sine theta t minus 1/2 gt squared divided by v naught cos theta times t. Actually, the first thing I'm going to do is reduce this. Every term has a t in it. So if I divide that out, I'll have v naught sine theta minus 1/2 gt squared divided by v naught cos theta. That's what equals the tangent of 5 degrees. So, and this is just a number. Now, in this expression, I know v naught, I know cos theta, or I can calculate it. So v naught cos theta and v naught sine theta are just numbers, and the only unknown I've got in here is t. So I can solve for that. Whoops, it's not a t squared anymore either. It's now just plain t, because I divided it out. So this turns into something it looks kind of scary algebra-wise, but it's not bad. So if I multiply out from underneath by v naught cos theta, I'll have tangent 5.00 degrees times v naught cosine theta equals v naught sine theta minus 1/2 gt. I'm going to move this over here and move this over here, and I'll get 1/2 gt equals v naught sine theta minus tangent of 5.00 degrees times V naught cos theta. And I guess I could factor out the V naught, but I'm just going to calculate these things as numbers at this point. And t, the time of flight here, is going to equal that whole thing divided by 1/2 g. Okay, that may look gruesome, but these are just things we can calculate. So I had ahead of time figured out V naught sine theta. That will equal, now remember V naught is 42.6. That's 42.5 degrees. So this ends up equaling 28.8 meters per second. V naught cos theta is equal to 31.4 meters per second. Oh, and I've got more room to work down here too. Great. Let's see, and oh well, I think I'll just rewrite my expression here. T is going to equal V naught sine theta 28.8 meters per second minus the tangent of 5.00 degrees times 31.4 meters per second. Tangent of 5 degrees isn't very big, so that's going to knock this one down by quite a lot. And then on the bottom I'll have 1/2 of 1.61 meters per second squared. And if you want to know why the acceleration due to gravity is less on the moon, stay tuned till next quarter when we study gravity. Okay, that's just a matter of plugging all the numbers into here. And when I did that, I got this, 32.3 seconds. Could you imagine that? Hitting a golf ball and having to wait for half a minute before it hits the ground. All right, well, that's only how long it's in the air. How far up the hill is it going to get? I can go to my x equation and position equation, and that's just going to be the x distance it travels, which will be the horizontal distance to this point under here, is going to equal V naught cos theta, which is that number. Well, I'll write it in variable form first. Cos theta times that t, which will equal 31.4 meters per second times 32.3 seconds. And that actually ends up equaling 1,020 meters. Now, when they say how far up the slope will the hill land, I think that to me means this thing here. And I just figured out this. But x over this distance, let's see. This adjacent side divided by the hypotenuse will equal the cosine of 5 degrees. So x over, if I call this d for how far it goes, x over d will equal cosine of 5.00 degrees, which is pretty close to 1. But that distance up the hill will equal x divided by the cosine of 5.00 degrees, which is 1,020 meters. It's not going to be a whole lot different from that, but okay, I get, well, 1,024 meters, but I've only got 3 sig figs, so may as well just call it 1,020 meters. Okay, it wasn't that different. That was a complicated problem. Again, we're just applying these equations of projectile motion again, whoops, these ones over here, again and again and again, this one we did have an additional wrinkle. Y over x is equal to the tangent of 5 degrees.